Hello, welcome to our second video on weak acid calculations. In this video, we're going to focus in on determining the pH of a weak acid. So if you can go to your question number 3. So here we have propanoic acid, which we're going to simplify again, this one with HPR, is we're being given the Ka. And in this case, we're going to be searching for or trying to find our concentration of hydronium and the pH of that weak acid. And we also have the concentration, the initial concentration of the weak acid. So just like in example 1 and 2, we're going to start with the balance equation. So we have our weak acid that's going to be reacting with water, which is going to act as our Bronsted-Lowry base. So the acid is going to be donating a proton to water to form our hydronium ion. And then we have our negative ion. That is just our conjugate base of our weak acid. We also have our Ka expression that we can go ahead and set up, which is the concentration of hydronium products over our reactants. Remember to leave out water, so we have HPR on the bottom. All right, so just like before, we're going to use an ice table to initially set this up. So our initial change and then our equilibrium concentration. I can go ahead and take water out of this. Again, it is a pure liquid. All right, filling in our initial information, we know our concentration is 0.10 molar of our weak acid. Our hydronium, we're going to be saying, is starting at 0, knowing that the amount of hydronium from the autoionization of water is going to be less than 5%. And then we also know that before the weak acid ionizes, the concentration of its conjugate base, the negative ion is going to be 0. And then we know that this is going to proceed to the right, so we can go ahead using our balanced equation and show a change of negative 1x to our weak acid, and then plus 1x for our products here. So then I'm going to make the combination here. Oops, that should have a little m there. X and X. Now in this case, we're going to be using our Ka to solve for a concentration of hydronium, or X in this case, and then going ahead with the rest of the calculations. So when we go ahead and do this, we're going to have our 1.3 times 10 to the negative 5. We have our X times X, and then here we're going to have our 0.10 minus X. And just like we did in our equilibrium unit, we're going to, and just like we talked about in our previous video, that change in X that we have, we're going to make an assumption that it's going to be much smaller or less than 5% of our initial concentration. So we're going to make an assumption here to simplify it, which we'll check at the end. All right, and then we can go ahead and solve for X here. So if I go ahead and simplify this, I would end up with X squared is equal to 1.3 times 10 to the negative 6. So multiplying, cross multiplying is what most of you guys probably did there. Take the square root of both sides, and then X is going to be equal to, keeping to the two sig figs, 1.1 times 10 to the negative 3, okay, which is equal to our concentration of hydronium. But I always go ahead and go back, fill in the rest of the ice table. And then based on sig figs here, we still end up with that 0.10 molar, which makes sense because, again, that change in X is much smaller than the initial concentration. So part of our answer here is that change in concentration, which we got 1.1 times 10 to the negative 3, which is one of the things we were looking for. And then our other is our pH, which, since we have our concentration of hydronium, we're just going to take the negative log of it. Which, keeping with the two sig figs, we're going to record as 2, and then the two sig figs come after the decimal, 0.96. I usually tell students, just because of trying to wait until the end to round, if you get this value for hydronium in your calculator, I would simply probably just plug that right in, but it's ultimately up to you. You could do it either way. So those would be our final answers, our hydronium ion concentration and our pH from the provided Ka. And then we are going to just check our assumptions here that we talked about in the last video. So we're going to check here that the amount of our weak acid that ionized, we're just going to show that that is less than 5%. which based on our numbers, you can go ahead and plug it in. You'll find that it is equal to, in this case, 1.1, which is less than our 5%. Check. And then we know that the other thing we're just going to show right now is that our hydronium ion concentration from the I spelled that wrong, sorry, autoionization of water, which we know that the amount from water is 1.0 times 10 to the negative 7 over the amount of hydronium from the weak acid, into getting 0.009%, which is definitely less than 5%. So both of our assumptions check out. All right, if you feel comfortable, you can go ahead and pause it, try out number 4 on your own. If you feel like you need a little bit more help, keep watching, or just go ahead and check it after you do your work. All right, so we're going to move right on to, in this case, number 4. All right, so here we have benzoic acid. It's used as a, I'm trying to get rid of that, food preservative. What is that concentration of hydronium and the pH given its initial concentration? And in this case, it's giving us the pKa, which we'll talk about in just a second. So let's go ahead and write our equation. I'm going to keep it how it's provided in the question. Just a little reminder, be on the lookout for that COOH. The hydrogen at the end is going to be what actually ionizes when it reacts with water. All right, that hydrogen is going to get donated to water here. So we have our hydronium ion that forms, and then we have our conjugate base of our weak acid, which will be C6H5COO minus. Okay, we can also go ahead and write our Ka expression. So Ka, which is going to be our products, which is our hydronium ion concentration, times the conjugate base of our weak acid over our weak acid. Okay, so let's go ahead and set up our ice table just like in our last one and start filling in our information that we know. Okay, we know our initial concentration of our weak acid was 0.25. Again, our hydronium ion concentration is going to be 0 because, again, that amount from the autoionization of water is going to be less than 5% of it. And then we have 0 of our conjugate base of our weak acid. It's going to proceed to the right, so we can fill in our changes of X. And then summarize the chart for our equilibrium concentrations. So remember, in this case, we are going to use our Ka, or initially our pKa, in order to solve for this. So just remember back from last week, and I'm going to just put this under here just because this is where I have space, that our Ka, we can find from our pKa, just like how we find our hydronium ion concentration from our pH, is we take 10 and raise it to the negative pKa. So definitely incredibly helpful to know that moving forward with the practice. So we'll have 10 raised to the negative 4.20, which is going to be equal to, keeping with the 2 sig figs from the pKa, just like how we use sig figs with the pH, we're going to have 2 times 10 to the negative 5. So there's our Ka. And actually, I'll probably just if we just take this, and I'm just going to plug this in down here. So here we have our Ka, which we're going to say equal to the expression. So we're going to have X times X over, we're going to have 0.25 minus X. And again, just like in the one before, we're going to make our simplifying assumption here, where we're going to say that that change of X is going to be less than 5% of the initial concentration of your weak acid. So when I go ahead and simplify this, I'm going to have X squared is equal to, and in this case, I'm trying to keep this going in my calculator. So if I don't try and round this off right away, I want to show you one of these. I would get this, and then, because again, I'm going to be able to use that for my calculator from my initial multiplication, and then taking the square root and keeping my value going in my calculator. And then at the end here, now I'm going to round it to the 2 sig figs. So 4.0 times 10 to the negative 3. Which, remember, is our concentration of our hydronium, which is one of the values we're looking for. And then I, again, always go up here, fill this back in for both of our X values. It's a good habit to get into because as we move forward with other calculations, knowing where all these values come from, and it's going to make it easier when we go to use them in multiple calculations. And then here we're going to be able to calculate that to be 0.25, rounding according to sig figs. So that gives us our concentration of hydronium here, and then we can find our pH, which is again taking the negative log of that concentration of hydronium. So then our pH, keeping with 2 sig figs, is going to be 2 point, and then our 2 sig figs after the decimal, 0.40. So we have our pH, and we also have our concentration of hydronium. All right, and then finally just doing those two little checks, which I'm going to simplify down just a little bit. Here we have our weak acid, which just because of the formula, I'm just right now going to write it as HA, that ionizes. Okay, that change is 4.0 times 10 to the negative 3 over the 0.25, which is times 100, definitely less than our 5%. And then if I check the hydronium concentration from the auto ionization of water, that's that 1 times 10 to the negative 7 over our concentration of hydronium from our weak acid, 4 times 10 to the negative 3, and that is also less than 5%. Okay, you can turn this one off, and then we're going to move on and do percent ionization to wrap up our weak acid calculations.